to start to catch up with you guys. That's roughly how they should look. Very roughly. So the height determined by the left endpoint. Just go up to where the left endpoint hits, where the left part hits, and then you draw over. Making sure you stop before. Then you have I got this for the left endpoints.
Kept mine in fractions.
What's up?
Kept mine in fractions. You're at 89 eighths. Same thing.
89/8.
Yeah,
Yes.
same thing.
Sweet. I like it. Yeah, this is not too bad. I mean, I don't have to lose any exactness doing this. You see, it's only when you have to cut a decimal, round it somewhere, cut it somewhere, that's when you start losing information. Then all those errors build on each other. Here, I don't lose anything. I mean, that's exactly what that is. Okay. So what about this one? You can redraw that sucker, but it's basically the same stuff from before. You're going to use all these plus f of 4. So it's all these minus that one plus f of 4. So it'll be 22.25 minus 1 plus whatever f of 4 is. F of 4 is. Well, it says f of 4 here is 4. Yeah, negative 16 plus 24 is 8 minus 4 is 4. Cool. So you guys, I don't know if you can understand. You could redo everything you just did. You could redo this whole thing, except that wouldn't be here, would it? If you did right endpoints, it would look like this. Maybe it'd be better to do it. 1.5, 2.5, 3.5. So now it would be this that determines the height. So we're going to start with this guy and draw back. Draw this guy and draw back. Draw this guy and draw back. Draw this guy and draw back. So now F1 has not a damn thing to do with this. But F4 does. I don't know if you start to see what I mean by when you do the left endpoint, you've done a giant chunk of the work you need for the right endpoint. So I can actually take the result I got for the inside, subtract the thing I don't want off, and add the thing I want, just to do the right endpoint, just to use the work I've already done. Or just redo the whole thing. Nothing wrong with that either. So what do you get here? I get 12.625. Is that what you guys got? Okay, I like it. For some of you guys will stare at your wrong answer going, yeah, oh yeah. I got it. And then when you average those together, 11.875. When you just average those two results together. Sounds right. 76, 76. There. Okay. Now, let me show you how to do this in ye old calculator. We're about to see, well, let me tell you something before I show you the symbol. Symbol a lot of you guys probably already know, but I just want to show you where it comes from. This is going to kind of bleed over into the next idea. To make this whole process better, what do I do? How would I get a better estimate than what I got right now? What would I change about the problem?
Change it to infinity.
Well, we don't have to go that far. I mean, if I just made it 10 instead of 6 rectangles, 10 rectangles, I would get a better answer. And if I made that 20, I'd get an even better answer. So that's the series of images in the book. Oh, where are you, images? Images. Low resolution, better resolution. Yeah. Low resolution, better resolution. Yeah. You can see how the white space that shows you the error is getting smaller and smaller for each increase in your number of rectangles. It's fitting better. Right? Okay, maybe. So what we want to do is we want to take this way of approximating the area. Like Marco said, you want to take this and make it have infinite rectangles. So you want the limit as n goes to infinity of this. Now, I've talked about this a few times in this class. What happens to delta x when you make it get really tiny? Because if you're making an infinite number of rectangles in a finite space, how wide is each one going to get to be? That's the question, really. So what happens to the width when they let them approach 0? They actually go to what symbol instead? This is related to the differential stuff. Yeah. They go to dx. The xi doesn't really make sense now, because if I have infinite rectangles, what that means is every x value is going to get used. If you really think about it, if I have infinite rectangles, that means that every x value is in one of those infinite rectangles. So every single one gets used. So instead of f of xi, I just have f of x. They're all going to get used, not some special ones. All of them are going to get used. And this symbol here, this idea here, this really is the truth here, by the way. They decided, it was Leibniz that did this. He said, all right, now, we're having a really huge sum here, because it's an infinite sum. So it's a big sum. So let's use a big letter S to represent that. So that's really where the symbol came from. It's an elongated S symbol. So this is the integral. Fundamentally, the integral finds areas under curves. Some of you guys already know that it's more than that, and there's something that I haven't tied that together yet. So these can be tied to the idea of antiderivative. We just haven't done that yet. Officially, their job primarily is to find areas under functions. How much area is under this function from whatever to whatever? How do we know so far? Is that? So this is just notation. If I let the double rectangles go to infinity, this is the notation I use instead. It's understood to be infinitesimals because it's got that little dx symbol in there. And this is the first time we're seeing symbols that are like bookend symbols. This goes with this. It's sort of like the square root. Where would I put something to put it in the square root? I wouldn't put it here. Now it's a ninth root. If I wanted the square root of 9, I'd put it inside the symbol, right? If I wanted to integrate 9, I'd put it between these two. They're bookends. They're one symbol, but it's a bookend symbol. Does that make a little bit of sense? A little tiny bit? Okay. The reason I make a big deal out of it is this is very important. You don't just leave it off and go, well, that's the only important thing. No, this is very important. It tells you what you're integrating with respect to. Which becomes really important when you start integrating with all kinds of variables in your shit. You don't know which one am I integrating with respect to. Now, let me go back and show you how to do this in the calculator then. If you go ahead, if you have the calculator, go ahead and do this. Rar. Put the function into y1. Bam. By the way, I can't remember if I showed you this. I don't know if you saw my little table I made. Woohoo! I made a table. But I can be very specific in my table by going to table set and making the independent variable ask. So then it'll ask me, what do you want? And then I can plug in whatever the shit I want to, and I make my own little XY table very quickly. That's very, very nice in a few different places. Stop graph. So you can do that. So if I want to know no sign, go away. 8. Tell me what the value is, so forth. Away. There we go. It's a little better. Okay, so now everybody do Zoom 6 if you're doing this with me, so we all have the same window. So that's the picture. That matches up with what was on there. And now I want to calculate something graphically. So everything about the graph is on the top, and I want to calculate. So it's right above trace. Calculate. And you can see now which thing I want to do. Which thing do I want to do? Yeah. And it's going to ask me, integrate from what to what? So I'm going to say integrate from 1, what was it? I forgot already. To 4? 1 to 4. Bam. Okay, I love that it shades it in. That's so kick-ass. Just to remind you, hey, this is what I'm finding for you right now. So it gets us 12. And what did we get? What was our best estimate? 11.875. That's, considering we only use 6 rectangles, and this is using infinite rectangles, that's pretty damn good. Your function would have to be really kind of freaky to need like 30, 40 rectangles to be a decent estimate. Okay. But in the end, it's still just an estimate. That's why we do want to get to infinite resolution. By the way, I don't know if you guys noticed this. You see number 6? What would number 6 tell me? What would number 6 tell me? What is number 6? What does that mean? Derivative. I like it. So it would tell me the slope at any point. So if I'm going to slope at 2, it tells me the slope is 2. Kicking the ass in. And I want to show you. All right, let me do one last thing with this. If I go to, see if I can do this here. I can't remember now. No, I can't. Damn it, I forgot how to do this. I'm not going to stand here and try to. Somehow there's, in one of these little sub-menus, screw it. I'm not going to try to find it. There's something called function derivatives. You can actually say, well, now I'm going to have to do it, aren't I? Here it is. Function, integral. Oh, I can't remember how this stupid thing works. Oh, well, too bad for us. Good thing I make you do it by hand. But you can tell it to do the derivative of y1. And it will graph that on top of y1. So make y2 equal the derivative of y1, and it'll graph it. Which is what you guys had to do. You had to graph, remember on top, you had to graph the derivative. So it's a good thing I didn't tell you that earlier. But there's a way to do that on here. Okay. You know, like, you got that backwards, Jeff. So we are going to do something kind of related to... No. The minute I say this, I'm going to have people... We're not going to get that deep into this. We're only going to do a couple of these. But we're going to do something related to like limit definition for derivatives. We're going to do a little bit of that for integration until we just start getting into the shortcuts for integration. But you have to see some of what goes into finding an infinite limit. You have to do a little bit of that before we just get into just doing it. So I want to tell you a few facts before we get into this process. The first one is really kind of cool. You can very quickly prove it. Oops, let's say I. It's be the same way as the book. I equals 1 to n of I. This is related to an urban legend in math. Nothing you'd want to make a movie out of. It has to do with a kid named Gauss. Some of you guys, I don't know, you know Gauss? His name is the unit of measure of strength of a magnetic field. So once you get like a unit of measurement named after you, you did some shit. All right, you did some stuff. Statistics, the normal curve is a Gaussian curve. He studied that before they realized it could be used for statistics. He just did the general thing. So supposedly one day his teacher, he was like 10 or something. This is all hearsay, but who knows? It could be true. And the teacher the class was just going crazy. The teacher's like, okay, sit down, add the numbers 1 to 100. And when you're done, you come up and see me. And he sat down, he started reading his paper. Oh, this will take him forever. Little smart-ass Gauss is over there. He does it in about 6 seconds. And he comes up, here it is. And the teacher's like, what the shit? And the teacher starts to do 1 plus 2 plus 3. Oh, God. Right? The teacher just starts doing it, and Gauss is just staring at him like, what the shit are you doing? That's some stupid stuff. I mean, that would take forever. 3 plus 3 is 6, plus 4 is 10, plus 5 is 15. I keep going. But there's a way to reorganize it. I don't know if anyone's ever seen this before. There's a way to reorganize it to make it much quicker. Something called repeated sums. What's 1 plus 100? 101. What's 2 plus 99? What's 3 plus 98? How many of those are you going to have? How many pairs will there be? 50. So it'd be 50 times 101. You have 50 pairs that add to be 101, so you end up with 50-50. That by itself is kind of neat. You add up the first 100 natural numbers, the answer is 50-50. You gotta like that shit, just on the basic level. Right, I don't care what you feel about math in general. You gotta like that's just neat. But bigger issue is, do you see how the n over 2 comes into play? If it's 100, I got 100 divided by 2. I got 50 pairs that will add up. And then the first number is 1 and the last number is n. That's the repeated sum. Now, to be honest, this works even if there is not just 1 between the numbers. If it was like 2, 4, 6, 8, 10, you could still do this process with that. It just has to be what's known as an arithmetic sequence. You have to keep adding the same thing. That's the sequence. If you have that, this will work. I like it. So somebody might say, well, what if you have an odd number of things, Jeff? You can't have you can't pair up an odd number of things, Jeff. So if I had to add 1, 2, 3, 4, 5, so there's 5 things, right? So this formula would say it's 5 over 2 times 6, right? Do you see how that one's even? That would always happen. In fact, look, it's 6, 6, and half of 6. So that's why that over 2 still makes sense. So sure enough, you get 1, 2, 3, 6, 10, 15, and 30 divided by 2 is frickin' 15. So that it works. Get out of there. Come on, 15. Okay. Is that cool? I mean, have you guys ever seen it before? Okay. And I love it when people are like, well, what good is that? Well, you couldn't do a whole bunch of shit without knowing this little simple thing. Right? On one level, it's just playing with numbers. On another level, it's like, now that we know this, we can do a lot of other stuff with it. Besides impress your friends at parties. Get out of here. All right. So you would think that maybe these next two would be directly related, but only one of them is. This one. So this would be adding up squares, like 1, 4, 9, so forth. You guys cooking? So this one is one I definitely don't have memorized. Now, there just is no easy way to show you this. There's something called mathematical induction. It's not joining some kind of society. It's just the name of this proof method, math induction. If you take 280, you will do math induction. It's just a proof method, and it's really not that bad. Everybody still hates it. Oh, I love math induction, but I wouldn't. So for example, let's check to see if this is true. All right, so let's go I equals 1 to 3 of I squared. So that would be 1 plus 2 squared plus 3 squared. And I get 14. Now if we plug some stuff in here, see if we get the same value, right? What would n be? What's n? 3. So it'd be 3 times 4 times 7 all over 6. Well, that's 12 divided by 6 is 2 times 7 is 14. So it's just a quick way to get the sum of these. And you'd think there has to be a quick way. There's a pattern to the numbers. So there's got to be sort of a quick way to add them up. You really kind of feel that in your gut, hopefully, a little bit. And then finally, the last one that's kind of nifty. If I add up the cubes of numbers, this is exceptionally freaky, you get this thing squared. Which has no really good, you can't be like, I expected that to happen. No, you didn't. And again, there's a proof method called math induction that would prove all of these. This one I basically proved already. You don't need that math induction, but it would handle this one too. All right, so that's one level. I've got a little handout that's got these on it too. I just want to do a little bit on the board, then I'll give you this handout, and then we'll try to do one together like this. What we're doing now is not just doing that process with 6 rectangles or whatever. We're going to do it with an infinite number of rectangles. And somehow we're going to do it in less than 10 minutes or something. Right? Sounds like a lot of work. So these are just little facts that we keep, that we just know are true whenever we need to use them. So let's try an example out. In fact, let's do that one that we just had. Let me see. What was the function? It was negative x squared. I've lost. What was the one we just were doing? Plus 6x minus 4. Okay. So if I want to, so here's the idea. I want to take limit as n goes to infinity, sum I equals 1 to n of f of xi times delta x. All right, so let's figure out each piece. See how this kind of comes together. And it doesn't really matter, but just so we have something to think about, let's think about this from the standpoint of left endpoints. So what's delta x going to be? Oh, I'm sorry, this was from 1 to 4, right? All right. So do you notice, real quick, what's the last thing I would do in this statement, mathematically? What's the last thing I would do? In this statement right here, forgetting everything else, what's the last thing I would do in this statement? Okay, so I would evaluate the limit last, right? I would let n go to infinity. I'd let that happen last. You guys with me? So everything I'm about to do is related to that guy because the last thing I do is going to let n go to infinity. So I'm not starting with infinity, thank God. They can't really do that. What's the definition of delta x? Just tell me. It's b minus a. So do we have n specified? No, it's not specified. I'm going to eventually let it go to infinity, but right now in this statement here, it's not specified. So what's my delta x? 4 minus 1, 3 over n. That's delta x. So you tell me an n, I'll tell you how wide your rectangles are going to be. Right now I don't know what n is. What about xi? So here's the idea with xi. So I'm going from 1 to 4. Here's my function. What does it look like that, sort of? So if I go to xi, so x1 would be, what did I say, left endpoint? It's a little bit easier, actually. I was trying to do right endpoint. It's a little bit easier to get into it. So x1 would be 1 plus delta x, right? Is that cool? X2 is going to be x1 plus delta x again. So, but x1 is 1 plus delta x, so x2 is going to be 1 plus 2 delta x. I think you see where I'm going with this. So what's xi going to be? No, I. 1 plus I delta x. Like the last one we do would be 1 plus n delta x, right? Okay. So, and now I can be even better. What's delta x? So this will be 3i over n. So it's 1 plus 3i over n. All right, so let's start to rewrite what we got here. We figured out what delta x is. We figured out what xi is. Let's plug in what we got so far. We got a lot of shit going on. Limit n goes to infinity. Sum I equals 1 to n. F of that times that. So now I just got to do this piece. This is the one last piece that I don't really have fully fleshed out yet. Right? And here's f. So let's see. So I get limit n goes to infinity. Sum I equals 1 to n of negative 1 plus 3i over n squared plus 6 times 1 plus 3i over n plus, minus 4 times 3 over n. Let me do this. Get this all together. So I just did this expanded bam, 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 times 3 over n at the end. Just plug that shit in because that's what it says to do. Now is this pretty? Not the most. Me, I'd say, yeah, that's freaking beautiful. But I understand most of us in this room would say, no, that's not pretty looking. All right, so let's see what we can do here. Limit n goes to infinity. Sum I equals 1 to n. You can FOIL this sucker out, and there's a negative on it, so it'd be negative 1, 3in, 3n, so 6in, so minus 6i over n. 3i over n times 3i over n is 9i squared over n squared, so minus 9i squared over n squared. All right, so that's just foiling and bringing a negative through. Is that, for that piece, is that cool? All right, FOIL that, you get 1 plus 6i over n plus 9i squared over n squared. Just bring a negative through the whole thing. Then I can distribute plus 6 plus 18i over n minus 4 times 3 over n. I think that's enough of those things. So good Lord. So let me see. I get 5 here, right? See, I got a 5 here, and then minus 4 is 1. So my whole numbers is 1. Is that cool? Yeah. Yes? Times 3 over n. So I get sum 3 over n. That's just this times 3 over n. Now let's look at our i's. I get minus 6i over n plus 18i over n is 12i over n. So you get plus 12i over n times 3 over n. Let me make sure everybody's... You see all I'm doing right now? This is just algebra right now. So plus 12i over n times 3 over n is 36i over n squared. Kind of sucks about the index being I is you don't think it's complex, okay? You don't have any complex stuff right now. Yeah. And then if I look at my I squared, I only have this one I squared term, right? So now when I multiply by that, I get minus 27 I squared over n cubed. So that's consolidating and distributing the 3 over n. Then, let me see, now I can break it up a bit. So I got sum equals 1 to n, 3 over n, plus sum I equals 1 to n, 36i over n squared, plus, minus sum I equals 1 to n, 27i squared over n cubed. Well, I found my e's just start getting really disgusting after a while. Now I know that most of us probably aren't as used to sigma notation, but hopefully it makes sense to add these additions. I can add the complete additions of e. I mean, this makes sense. It doesn't matter what order I add it. Just using commutative property here. It's a bunch of additions. So yes, it does look like the sum distributes, if you want to remember it like that. But it's not really what's happening, but what the hell it looks like it. Now, this is really important. This is going to relate to something else we got to be really careful about with integrals when we get fully into integration. This sigma notation, what is the variable for it? And what's a constant? What does this guy consider a variable, and what's he consider a constant? I and n. Which one is the variable, which one's the constant? What does this mean? I equals 1 to n. That means that I is taking on the values from, do this, we just did this earlier.
From 1 to n.
1 to n. So isn't I the one that's varying? Isn't I the variable? And isn't n some set number? So n is a constant. All right. So that means I can do this. I can take 3 out. I'm sorry, I can take the whole thing out, actually. That's what it is. So n is a constant related to the summation symbol. Plus, so over here, what's the only thing I can't take out of there? The second one. What's the only thing that's not a constant according to this? I. So I get 36 over n squared I. Minus 27 over n cubed I squared. And now you start to see why I was talking about those summation rules, right? I can replace this with n times n plus 1 over 2. I can replace this with all that gobbledygook over 6. So this is kind of huge. Which one of these, what's the thing in this whole thing that sees n as a variable? The limit. Am I taking that yet? No. The summation symbol sees n as a constant. Because it's adding from 1 to n. N has to be a constant for it. Now I am letting n go to infinity eventually, but I'm not doing that yet. N is a constant for the summation symbol. All right, now, can somebody tell me, if I add up 1 n times, what do I get? If I add 1 plus 1 plus 1 and I have n ones, what do I get? If I add up 1 3 times, 1 plus 1 plus 1, you get 3. If I add up 7 times, you get 7. If I add up n times, you get n. 1 plus 1 plus 1 plus 1 n times is n. Okay? So then I can rewrite this. Oh, you guys love this shit, man. You're like, oh, more than 10 steps? That's my kind of problem. 3 over n times n, that is n. We just figured that out. Plus 36 over n squared times this guy I told you earlier, and I've got it on a little handout too to remind you guys, and you don't have to memorize it, don't freak out. I'll give it to you if I want you to use it. N times n plus 1 over 2. Remember that? We just did that one earlier. Minus 27 over n cubed times the weird one that I always forget. N plus 1, 2n plus 1, all over 6. It's kind of running into that. Holy shit, Jeff. Are you serious right now? You're in calculus. So yeah, I'm serious. All right. So now, look how beautiful this shit is. Please, can anybody see how beautiful this shit is? This goes away, so the limit is 3. Yay. This, what happens here, 2 goes into 36 18 times. Can anyone see what the limit of this is as n goes to infinity? What's the top? N squared plus n over n squared. What does that do as n goes to infinity? This is n squared plus n. The powers are the same. So as you let n go to infinity, the answer is the ratio of the coefficients, right? If I let n go to infinity, how important is n related to n squared? Not. What's n squared divided by n squared? 1. Okay, so it's 1. Minus 27 over 6 reduces to 9 over 2. And again, the same thing happens here, but what's the ratio of the coefficients? 2n cubed over n cubed, so that's going to be times 2. So all I'm doing, what's the limit as n goes to infinity of 2n cubed plus shit all over n cubed? That limit's going to be 2. Yes, that's it. That's all that's happening. Well, I won one person over. Okay. Wouldn't this be 2n cubed plus lower powers? Right? If you multiplied it out, don't multiply it out. That's bullshit. Don't multiply it out. So what's the limit as n goes to infinity of 2n cubed plus other shit lower than that over 1n cubed? It's 2 over 1. It's 2. You know that shit from pre-calculus.
No, I was just like confused because it says like n cubed on 27 over n cubed. So then why isn't it the n to the n plus 1 the bracket? You know what I'm talking about?
Where will you start?
To the top, right. Yeah. If it's n cubed on the left side of it, wouldn't it be like the summation of the I cubed? Or why did you use the square instead of cubed? Oh.
Well, yes, this guy, which is this thing, right? There's no I cubed anywhere. That's okay.
Yeah.
And then what do I get here? I get 3 plus 18 minus 9. 21 minus 9 is 12. Wasn't that the exact answer we got on the calculator for that? Do you remember that? I feel like I think I was born in this room. I don't remember anything. When we did it on the calculator, we had it shaded in. Does anyone remember that we got 12? It was really close to our 11.875, whatever it was. You're all like, oh, it's really close. Well, now this, of course, is why is this perfect? Because we used an infinite number of rectangles to do it. So it's going to be perfect. It's exactly the answer. There's that much area from 1 to under that curve, from 1 to 4. That's kind of nifty. So this is sort of analogous to the pain of the limit definition of derivatives. Obviously, it's a little more painful. That's why I don't do a ton of these. But I have got to show you at least once or twice what is really going into these things. So let me give you this handout. This kind of captures, this has a different example, so you have something to reference when you're doing homework. Colorful and all that kind of stuff. So I want to talk about just a few properties of integration. So again, this is just, there's nothing on here for you to do. I just want to give you another kind of fully worked out example. Can you, this might be a little bit weird to ask, but this here, I think I forgot this earlier. Let me rewrite this again because I think I forgot that at home. Yeah. So we were just discussing this idea. When I left off, what's kind of hidden, it's hidden here, but still, it's on me to remember this. This is what's known as a definite. It's a definite integral. Because what was this going from to? It was going from A to B, remember? And that's, of course, what we figured out what delta x is using that b minus a over n. So this has got to be from a to b, sort of mimicking this. So this would officially be called, you would say this is the integral of the function from a to b. So a way to draw this would be, you know, just general, it would be like I had earlier. Here's my f. Wah! There's the integral. Now what's really funky about this is that's the area under the curve. What would happen though if my curve looked like this? I didn't have to make it all funky, doesn't matter. It could just be, oh yeah. What kind of area do I get? Negative area. But I really want you to understand, this is, how do I say this? So if this was like flow rate over time, and this was time, finding the area would be finding the total amount that flowed. This is water or something. Let's say it's water, right? Water. So this axis is flow rate, and this is time. When I find the area, I'm going to find the total amount that flowed during the time. Now, couldn't it be something like it flows this way, and then it flows that way, and it flows this way? So maybe direction is negative or positive, and that's why we might have negative area. So it isn't truly physically negative area. The same way that velocity being negative doesn't mean that I'm suddenly like inverting or something. It just means I'm going the other direction, right? So there's a huge thing, I don't really get it myself about, it's not really negative area, and oh my God, and it's bullshit. Yeah, of course it's negative area. Why not? Because the negative could mean a direction. It's not like negative physical area. I got a box with negative area. I'll get sucked into it. No, that's not what's happening. Are you guys understanding what I'm saying? So I mean, obviously, so then if I had something like this, this would mean I have a lot flowing out and then a little bit flowed back in. Right? That's all that would mean. So of course you would subtract that from this. So then of course it's acting as if it truly is negative area. It's taking away from this area. So the area from A to B would be a little smaller than the area from A to whatever the hell this is. This is like, let's call it C. Because that would subtract. That area from C to B would subtract from the other area. Because I'm losing stuff at that point. So maybe this is like cash flow, right? Over time. Yeah! Oh shit. Kind of happy that it came back up instead of going, what? Or maybe. The idea of flow rate really makes a lot of stuff make more sense. Okay, so what if I did this? What do you think about, it's kind of related to what I just had up here. I want to do it the same way. How do they put it the same way? Yeah, there. Okay, yeah, that's how they do it. Yeah. See in the middle? So let's say let me give you a situation where we would want to do this. This is maybe a piecewise function, right? Do you see that? Like it's a little, let's make some kind of dampened cosine, dampened sine, whatever. So if I want the integral from a to b of this piecewise function, I want to break it up. The area under this curve is the area from a to c plus the area from c to b. Right? So how could I rewrite this? It would be integral a to c plus integral c to b. Because this guy is really, if it's piecewise, it actually is two different functions, depending on which interval I'm looking at. Are you guys? So if f of x equaled y1 from a to b, and y2 from b to c, gather. Then this would be y1, this would be y2. I actually just plug the right functions into the right place. the right pieces of that piecewise function. Maybe. But this is a general rule. This is true, period. You can break up any function you want to at any arbitrary point and have it be two areas combined. But this is one place where it kind of makes sense to do so. Does it make sense to do so? Oh, what about, some of these are stupid. Yeah. What's the, can you draw this? I love, C is a constant, by the way, in this case. C is almost always a constant. Kind of makes sense. What shit would that look like? What did I replace with something else? What's the normal one look like? That. What's it look like now? So what is f of x? C. So can you draw this? Can you draw it? What's the x-axis look like? The line, Jeff. Yes. But what's on it? A. B. Right? A could be back here. They could both be back there. It doesn't matter. I'm just drawing a general representation. What does this look like? What's f of x equals c look like? What's y equals 3, for example, look like? Straight line, exactly. So it's going to be... That is a frickin' rectangle, right? So there are some problems in here that say interpret, draw this and then find the answer using geometry, meaning you'll end up with triangles or rectangles or some shape that you know the area formula for. So once you draw it, you're like, I don't need calculus for this shit. It's just 1/2 base times height. Sweet. Here, it's just, well, how long is it? B minus A times how tall is it? Yeah, so it's C times B minus A.